Welcome everyone. My name is Ritwik. I am a machine learning engineer at Pioneer Search, which is an open source or semi-open source company for machine learning, deep learning, computer vision related blogs and education resources. So we are going to be talking about JAX. Now this is our TensorFlow user group meetup. Shayad did a talk on you don't know about TensorFlow or lesser known stuff about TensorFlow, and we are going to be talking about JAX. So what's up? Well, JAX comes from Google, so we are hoping no one's going to notice and no one's going to mind, as long as we don't slip into PyTorch. Am I right, Shomik?
Absolutely.
Cool.
Well, I thought PyTorch is also a framework maintained by Google.
Okay, well, but we are not going to go there.
Okay.
And here are the authors. Shomik, who works at Weights and Biases, is going to be talking about a part of the talk, but me and Aritra are going to begin. We are going to be introducing JAX, opening it up to the floor, and then Shomik is going to be taking us through our training loop written in JAX.
Is it a waiting photograph?
It's a fancy restaurant.
Oh, okay.
Cool. So this is what we are going to be talking about: evolution of JAX and its power tools. Like, what are the basic things that you need to know about going into JAX? Where did it come from? Why a new library all of a sudden? And some of its power tools, some of the tools that you will need to speed up your workflow to work better in JAX, and we'll see how it all comes together in Shomik's talk. So this is the collab notebook that we created, and to make matters simple, this will also have to double as our slide. So Hiya. Let it connect. It's Saturday for Asia. Cool. So yeah, as long as So we, as I was saying, I was going to go through evolution of JAX. And you don't need to note down anything. All of this will be open source. It is open source. You'll get it. Okay. So we are going to talk about where did JAX come from, and to put it very simply, JAX comes from two parents, right? And ignore this imports and setup for the time being, because anyway you will run through it when you get the collab notebook. So this is what we are going to be covering. These are all the chapters. What is JAX? Autograd, XLA, what are they? What is JAX again? Why Autograd and XLA gives birth to JAX? What is the API layering of JAX? How you go into JAX and use stuff? And how does JAX measure up as a numerical computation library? And some basic code snippets in JAX.numpy and JAX.max. Don't worry if this is not really transparent right now. We'll go through it as we go through the slides.
I have a question.
Yeah.
Why install Autograd separately?
So this is not JAX will always have Autograd installed inside it. This is not to show that you can use Autograd inside JAX like this. This is to show that how Autograd and XLA comes together and gives birth to JAX.
Okay.
It's like an introduction to where JAX was born from.
Like a precursor to JAX.
Yes. Thanks. Whatever he said.
I said chicken biryani.
Okay. So what is JAX? As I was saying before Shaida said that it was a precursor to JAX. JAX is basically Autograd for XLA. That is simplifying matters a lot, but that is what we are going to run with, right? And to those of us who are new in JAX or who are not really, tangled with JAX that much, we didn't know much about JAX. Now we know nothing about two new terms. So what is AutoGrad and what is XLA? Fortunately, Shagda's talk already covered XLA, so we are just going to fly through that. But AutoGrad and XLA are two really great components, two really great things that come together and that builds JAX, right? And we already know a little bit about XLA. What do you think AutoGrad means? Automatic differentiation. Great. Now, there are, as we know, there are a few ways to do automatic differentiation, right? Few ways to do differentiation. Let's keep it at that. There's the manual way, hard code with your pen and paper, looks super cool, not really useful for a computer, right? There's the symbolic way, or everything that you do with your pen and paper, you create those into symbols, and you then put those symbols into the computer and run a program that mimics whatever you were doing with your pen and paper. That is useful to some extent, but then it will eventually lead to something called expression swell. So your expressions, because of chain rule, it will grow to a longer extent and then it's basically useless. There's the numeric way, which is again a little more useful. You use the finite differences or Ronju Kutta, I don't know. I'm not going to try pronouncing it, but whatever that was, you do that to solve differentiation. And that worked till a certain time. But after that, the star of the show is automatic differentiation. And let's be honest, if there was no automatic differentiation, we would not have existed as deep learning engineers. No one had time to go through all of that and do it numerically or symbolically or whatever. Okay, not any human beings, I think. So we know what AutoGrad is doing, right? It is doing automatic differentiation, and we have a few blog posts at Python Research around automatic differentiation. We will link to them through Rishiraj, but if you want to check out how automatic differentiation works, old school style, like Andre Karpathy does, we have created a few blog posts. You're very welcome to check that out, but let's keep that out of the scope of this talk. So AutoGrad is our automatic differentiation library, and to make matters simpler for us deep learning researchers, there's a light wrapper called autograd.numpy, which kind of moonlights as a NumPy-ish wrapper, and you can use NumPy-ish code semantics through autograd.numpy. Okay, and we'll see this this is a very common pattern. We'll see this in JAX.numpy as well. So, and the actual automatic differentiation will be helped or will be you can achieve that through autograd.grad, really convenient name there, and autograd.elementwise grad. So, without further ado, this is our function. Very complex one at that. And what we are going to do is go through automatic differentiation of this one. Before we do, anyone wants to hop in and say what the actual differentiation of this one would be? Great. I got that right. So, you got that wrong. You put in X. Okay. So this is a function that does what it is supposed to do. It calculates a square, and just to check it, we see that when we run it, it says, and I'm not running it. I hope this works. Also, we'll be going through and getting all those import errors later on, but I'm not running it right now. We pass in a value, we get the square of the value, pretty straightforward stuff, and then we want to calculate the gradient of that function, right? So what we do is call the grad function, and we pass that function through the grad function. Cool? And then we have a point. Whatever differentiation, automatic differentiation we are doing, let's imagine a number line or an XY plane, and we are taking a point, passing it through that gradient or differentiated function. So now this point is 1, and the gradient of the square function is 2 because it's supposed to be 2x. Everyone on board with me till this point? Good. Good.
Grad function की integration actual data like it was done on flows. Will it work for point equals to 1?
Yeah, it is supposed to work. Now, this is like it's a point, but as your question, what's your name? Dithan. As your question was about a different data type, let's not worry about different data types as much because that is like number 1 on your checklist to solve when you're creating a new repository. But number 2, 3, 4 would be to make it compatible for batches of data, because like let's be realistic, we are not going to go anywhere with 1.
Yeah.
So we need to have vectors which we can eventually pass through that gradient function. So here we are creating a vector, and we are printing the value of as we pass that vector through our function, which is x squared. And we see that as we pass all of the points like 1 to 9 through the function, we get it squared, and we are now trying to find out. Whether we can call grad function on that vector, and turns out we can't. What about? So what is happening here is that we just can't use grad function for this one because it's a vector, and we need to use element-wise grad function. So we define the element-wise grad as basically E grad, again really convenient.
How E grad was yes? How it was imported?
Element wise grad as E grad.
Okay, sorry.
I just skipped over the imports. Okay, so we put that in our code. We now create a E grad function, and voila, works, right? And that's just a basic overview of how AutoGrad works. Welcome to play around with the repository. We've installed AutoGrad for you, but there's also a very simpler repository created by Andre Karbati called Micrograd, and that makes it very simple for you to understand automatic differentiation.
It's a simpler version of that same, but it's more complicated by George Hurst, which is nanograd and micrograd.
Yes, don't go into that.
Tiny grad as well.
Very welcome to go into that, but at your own risk. So we talked about one of the parents here, AutoGrad. Makes our life easier. We basically need automatic differentiation for all of our machine learning, deep learning workflows. But what about the other part, right? What about Excel? And fortunately for me, Shagda has already covered immensely into Excel, so my task is now easier.
Here's a question.
You showed that E-grad, the grad works with X and E-grad works with vector. What about tensors or even higher dimensions? Will it work?
Yeah, absolutely.
That E-grad will only work.
Yes.
So what exactly is grad used for? Only for
Well, you will have constants and numerics at certain point of your time. You won't always have to work with vectors or tensors. You'll also have constants. You'll also have things that you need to iterate over. Scalars. Right. So XLA is like it stands for accelerated linear algebra, and as like Shagda has already mentioned, it is a domain-specific compiler that accelerates linear algebra operations for us, and it's device agnostic. Put the same compiled code into CPU, GPU, TPU, it works with all of them. So with that, we have something which helps us with automatic differentiation. We have something which speeds up linear algebra operations for us. We put them together and we create a new numerical computing library called JAX, right? And before we start, multiplying matrices and backpropagating through all of them and all of that good stuff, we need to first understand how the layering of JAX works. So API design of JAX is done in a way that the high level API is JAX.numpy, which is which helps in your numerical computation workflows, and the lower level is JAX.lax, right? And lax is as mentioned earlier, it's a lightweight wrapper around Excel. Okay, so and fun thing to notice here, did you notice that lax is an anagram of Excel? I didn't. Also pointed that out for me.
Is there a reasoning behind it? Why not call it the JAX.xl? Because it does not sound fun?
And it's already there. It's already there registered in Google because Excel is already taken the namespace.
Yeah.
Hence
So
LX.
why not use JAX.xl?
I don't have a Twitter account named Singularity Matrix. I can't
Double D.
I'm gonna have to brutally teach you at some point in time. Cool.
Double. And so if you have heard about the official documentation of JAX API, you'll see some packages listed, and these would be JIT, automatic differentiation, which like grad, as Shraddha was pointing out, you have that inbuilt inside of JAX. You don't need to import autograd from somewhere else. Vectorization and parallelization. So all of this will be taken care of by Aritra. I'm not going to go over that. I'm just going to let you in on JAX.numpy, and let's see how JAX.numpy works for us. Again, some basic imports at this point. Something to notice, something to keep in mind, and this is something that, as you mentioned, Singularity Matrix, who is Matthew Johnson and Jake Fidibi, they kind of reiterate about this through their documentation, is that it's not just a deep learning framework, it is a numerical computation library, and it just so happens that deep learning as a science falls under the category of numerical computation. But if you want to do physics-based stuff with it, or just general hardcore numerical computation stuff with it, JAX is your thing to do. Like invest your time learning JAX, because it will really make a difference for you. So
You can even create a game engine using JAX. Yes.
Okay, so before like handing it over to Aritra, going through some simple stuff in JAX.numpy. Anyone who is familiar, and I'm guessing like most of you are really well versed with NumPy, right? Because, okay, but you'll get there. So NumPy is really easy to learn. Go to the documentation. It's super easy to understand, and the documentation is really extensive. Not like well, can't name names, but but yeah. So go through NumPy. It's really easy to understand. And for those of you who are somewhat versed with NumPy, JAX.numpy mirrors it, really accurately.
Why not just say JAX? The
Well,
documentation is not like JAX. Why not just say that? Speak it out.
Okay, so there are a few key points of differences with JAX.numpy and NumPy. These are some things that you need to take care of or keep in your mind, or scribble in your notebook if you are going through JAX workflows. Let's go through them one at a time. So we are first building an array. This is a JAX array, and this is different from NumPy.nd array. Okay. Interoperability is somewhat possible, not recommended at all. You first create an array, print that array out, then you create a NumPy array and a JAX array. And what we are trying to do is we are trying to put this value inside this position in the NumPy array, living dangerously. Now we try to do the same thing with the JAX array, and big error message for us. Now, why is that happening? Because JAX doesn't allow your arrays to be mutated, immutable arrays. Okay, so if you need to do that, if you need to mutate your arrays, if you need to putting values at a place where in your workflow you need to get something in. So this is what you need to do. At that position, you set that value, and then you print out that mutated array. And notice something: this is creating a new array. You can't do that with the same array. And this all ties back with the JAX, mythology of having pure functions and pure workflows. Aritra will be talking through that. I'm not going to go through that right now. But basically, if you need to mutate anything, if you need to put in values at a place where it's not allowed, this is what you need to do. Index out of bounds, favorite error message. What we do with NumPy, the same NumPy array, it was created from 0 to 9, 10 values. We are trying to index the 1000th position, should return a value, right? Right? No, I was testing you guys. Thanks, Aritra. Cool. So it gives an index out of bounds error for the NumPy array, which is how it's supposed to be in normal world. Now let's try it with JAX array. It returns the last position. Something that we need to keep in mind if we don't want to, and like this is called failing silently. You don't even know that this has happened. But this has happened somewhere in your workflow and you have no idea.
What
and indexing is capped in JAX. So this is something that you really need to put in your mind if you don't want to suffer a painful death, and by debugging and not by anything else. And this is kind of fixed right now. It's discussed in this issue 9839, where they are going to return NaN eventually. The issue is still open, so I'll leave it at that. And that's the end of basically my part. All of this is actually a blog post. It's free, open to read at Finance Search. If you are really generous with your finances, subscribe to Finance Search University. You'll get all of these blog posts before everyone. You'll get the videos for that. You'll get the collab notebooks. But for everyone else, the blog posts are super detailed and it's open and free to read for everyone else, and it's supposed to stay there. With that, I'll hand it over to Aritra, who is going to talk about the fun stuff.
Hello. Okay, so right after Ritwik talked about how we are going to understand JAX, right? So my talk will basically be about JAX and the power tools of JAX. Okay? Very simple stuff. Now let me ask you this question: what is JAX? He told you the answer. What is JAX?
AutoGrad plus Excel.
AutoGrad plus XLA. I'm going to use the board if that's possible.
No one can see.
No, everyone can see. I just can everyone see? Does this work? Oh my. Can everybody see this?
Yeah.
Okay, so this is JAX.
No.
Not visually.
Yeah, 100 camera.
Now
You are gonna have.
Don't
increase the font size.
No, I just write this. AutoGrad and XLA. This is something which we need to remember. Okay? Achha, AutoGrad is a Python package. XLA is a compiler. Two things. Now, why did we cover AutoGrad in the first blog post? Let's talk about blog post now. This is the thing that Ritwik covered is part 1 of JAX series on Python Search. Part 2 is what I'm going to cover. Okay? So AutoGrad is a Python package. It's created by an organization called HIPS, right? It's not updated, but people still use AutoGrad, and it was created by Matthew Johnson, who later moved on to Google to create JAX. It's as simple as that. So if you understand AutoGrad, you will definitely understand JAX, and that is how we went about doing the entire series in Python Search. We first went into that Python repository, we understood what AutoGrad is, how AutoGrad works, how automatic differentiation works for that matter, and then we went into JAX to just understand the similarities of AutoGrad and JAX. Make sense to you all? Right? And if anybody wants to scribble, I am the person who would encourage you all to scribble in your notebooks or even create just a keep note and note whatever I am saying. Certain stuff that I am going to say is very controversial. Please don't tweet that out and don't adderate me, please. So what I'm going to do is, the first part is about important functional transformations. Now coming to important functional transformations, we need to understand what functional transformations are. These are all the slides that we have created for our video. It's not even interesting.
What?
So what functional transformations are?
Or can you close that little footer? It's very annoying.
Better? So what are functional transformations? There is something called transformations where we transform something to something. Right? In maths, most of the times if you read papers, you will see there is this two sign, two symbol. There is this domain, there is this map to something. That two sign is the transformation. Now I'm talking about functional transformation where the domain is a function and the part which gets transformed to is another function. Does that make sense? Funders, yes. So what we are trying to do here with my talk is understand why JAX kind of talks about functions so much. We'll come to this part later. Just imbibe this, that in JAX there are a lot of functions and nothing of the object-oriented programming paradigm as you have learned in your college, right? So functional transformations is one function to another function. You transform one function to another. Why do we require it? Something like this, fx is being transformed to gx. Before going to that, let's talk about a little caveat called pure functions. Why do we need pure functions? Is because JAX loves pure functions. Why does JAX love pure functions? Ask somebody else. All the input data is passed through the function parameters, or the results are output from the function results. This is what a pure function is. So most of the times, not most of the times, let's say all the time, this is what is written in the documentation. All the times you provide the same parameters to the function, you are expected to get the same outputs from the results. That makes a function pure. Does that make sense? So a function, you put in the same parameters, you get the same results. No randomness, nothing.
No print lines.
No print lines as well, because that prints out to an stdio, which is also sometimes stateful. That means your results can be hampered. So nothing of that sort. And this itself is a very contrived idea to have. You are not taking any state into account, which is kind of very rough for us who always love states, because we come from Java, we come from C++, where states are something which we love, right? We hold on to states, we change the states, we update states, and we print out states. But this time around, we are not working with states. How do we drill this point down? Let's have a checklist of pure functions. So you can read out the checklist. So all the input gets in from the parameters. That's the first checklist, like the first point. Second is all outputs are returned from the function. So there needs to be outputs, there needs to be inputs. That's a function basically. And upon sending the same inputs, the result should be the same. I'm iterating over this point again and again so that everybody in this room knows and drills this point down to the last minute cell of your body. That a pure function is something where the same inputs are going to give you the same outputs. With me, everybody? Now let's talk about stateful and stateless. So what happens here is that there is this class called stateful, right? This is a basic object-oriented programming paradigm. Everybody here understands object-oriented programming, right? So stateful, we have a constructor, we have a state which is initialized to 0. So as soon as you create this stateful object, there will be a state attribute to it, which is defined with, which is initialized with 0, right? Now there is also this change state, which takes self, as in the object itself, takes the self.state, that is the state that it already has, and then updates it with 1. Now there is this important point where I wanted to, which I wanted to point with the 2 lines, that this is the first line and this is the second line. So we don't always update the state only and don't have an output. The output and the state can be different. It's a very simple idea, but you have to understand this, because sometimes what we think, what we end up doing is, we understand, okay, this is the state, this is the thing that is going to be output. That's not the case. Sometimes, if you think about it in a neural network perspective, the states can be weights and biases. The output can be the output of a layer, which is not the weights and biases, right? Does that make sense to you? So this is the state changes with, updates with 1, and the output is just the square of that state. And what we get in output is the output. With me, everybody? So what we do with this statement is we initiate or create an object, right? And if we print the initial state, it's going to print 0. Now here, what we do is we get the output of this object called stateful, and what we do is we just call the change state. So what will happen? The state will update, will return an output. So you can print the output, which is 1, and you can also print the change state, that is the state that is being updated. So understand how this is stateful. The paradigm is stateful. That means you have a state, you can update that, you can make a lot of changes. So it always has something to do with states. With me, everybody? How do I change that to being stateless? We don't need states. JAX does not like states. How can we make change? How can we make this stateless? We have the same class, we have the same function. What we now do is we get that state out of its internal state. We provide the state as a functional parameter. What changes? Nothing changes. We just have to load that state. We have to create that state on our own. We have to pass that state inside of that function. The function of the class does not care what is coming in. It does not know that the state exists. Right? So it's stateless now. The class is stateless. Nothing changes, just that we have to create our own state. We have to handle the states on our own. The class is not going to take care of that. Right? Now, upon publishing this entire blog post, we shared this with the JAX team. The JAX team came us with a bashing answer. The JAX loves states. What is wrong with you guys? JAX loves states. This is not how it's done. So we asked them, what can we change? They said, try doing this. So what happens now here is that we still have state inside of that class. What happens now is that when we return this updated state, when we call this updated state, it acts as an immutable class. So once you change state, it creates another instance and gives you that state of the new instance. So what happens is you don't have this one object wherein the states change. You have this another object created with a changed state. That is what JAX does. So we understood while doing this blog post that we were wrong. JAX loves states. It's not actually how stateful or stateless your objects are. It's how pure your objects are. Does that make sense? So we did apologize inside of the blog post. We also mentioned the credits from the JAX team itself. We said that this is how it's done, and pure state is the way to go. We just kept the stateful and stateless definition still there because we found that useful. Because people need to understand that JAX does not really like pure states, does not really like controversial. Take it out of that video. Controversial statements. So it kind of comes to a point where you have got to understand what you need while you are doing JAX. It might just be that you need states. How do you imbibe that state inside of that class is up to you. We gave you 3 options. Something will come out of the 3 options. That is my guarantee, right? Make sense till now?
How did you lead to pure state class?
Pure state class is
What is the precursor to the pure state?
oh, pure state class is the stateful and the stateless classes, where the change states are the states inside.
Basically, they are idempotent.
I'm sorry.
Basically, they are idempotent.
Yeah.
The stateless.
Yep. Cool. Now let's talk about a communication language that JAX developers have built, and this communication language is called JAX PR. It's not a pull request. It's just JAX PR. That is how they are named it. I don't know why. So it's actually JAX expressions, which is abbreviated to JAX PR. So why do we cover this in 5 message blog post? We covered this because we found that while you have a function, and also iterating what Ritwik said, JAX is not a deep learning framework. It's a numerical computation library, not a framework itself. Just the fact that deep learning or people like JAX is because deep learning falls under this category of numerical computation. That is why we use JAX, not the other way around. JAX is not a deep learning framework. TensorFlow is. Does it make sense? PyTorch is. JAX is not. JAX is very vast. Hence we have FLAX, which is a deep learning framework. Optax, which is an optimization library. Okay? Make sense? So what the JAX developers did is that a JAX transformation or the transformation that we are talking about from a function to another function, JAX loves doing that. Why we covered this transformation is because grad, JIT, all the power tools, grad, JIT, VMAP and PMAP are all functional transformations. That is, you give these functions a function, these functions as in JIT, grad, VMAP and PMAP, some function, it will transform that function into another function and give it to you. It's not an object that you pass in, it's not a scalar that you pass in, it's a function that you pass in to these functional transformations, and the functional transformations are going to give you a transformed function, right? And how do we do this? This not interoperability, let's just say transformation. How do we do this? We do this by tracing all the operations there are, fusing them, sometimes understanding what they are, and to help us as in human beings to debug how these transformations work, there is something called JAX PR. So I'm going to blatantly read this out. A JAX transformation transforms a Python function into a small and well-behaved intermediate form. So it's an intermediate form that is then interpreted by the transformation specific interpretation rule. So think about these transformations specific to be your JIT, your grad, your VMAP or your PMAP. So it's very specific to the thing that we want. We are going to cover all of that, PMAP, VMAP, JAX and grad and JIT. The point here is that every Python function gets transformed into an intermediate form. That intermediate form then again gets transformed into something that we specifically want, right? This intermediate form or this the Python interpreter distills the essence of Python function into a statically typed expression. This expression that is being created inside of this entire process of functional transformation is known as JAX PR, right? And why did we try, and we are not going to cover this, why did we try to take a hit at this JAX PR is because nobody did. In the entire documentation of JAX, there is a very beautifully written documentation of JAX PR, but what I feel, again controversial, is people who already know JAX are going to come to JAX PR and say, hey, I already know this. But somebody who is beginning with JAX will never understand that documentation because it's very contrived, it's very filled with jargons. As soon as you are well versed with JAX, you are going to understand what JAX PRs are. But at Pi Message, what we did is take this other way around approach, where we are going to tell you, hey, this is JAX PR. This is going to help you. Read up, go to JAX PR or go to JAX. That is what we are trying to do. So this is an illustration which is built by Ritwik. What we do here is that we understand how to communicate or understand a JAX expression. It is very contrived for that matter. What we do here is JAX PR. Can you see this? Is the illustration visible to the backbench? Yeah. So once you have a function and you tell JAX to make a JAX PR out of it, you will have this part as something that is being output. We will see.
Is it a skeleton of any generic function or?
Yeah, it's a skeleton of any generic function that you provide to make JAX PR. That is the API to create a JAX PR. It's a generic thing. So what we did with our illustrations is that we wanted to communicate the grammar of JAX PR. So it looks basically like this. So JAX PR, there is this double colon equal to with a dictionary kind of a setup, where you have this lambda var star and var plus. Var star is a list of constants that the function provides, that is going to be listed out, and star or plus is whenever you have a collection of things. That is how things are documented inside of JAX itself. So star plus again star. So var star is the list of constants which are also called constants. Var plus is a list of inputs called inverts. So a function has inputs, right? That is what we know from our maths classes. So a function always has f of x, x is the input. So if you have f of x, y, z, blah 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 blah, this collection is inverts. If you have a constant inside of this function, goes to constants. Make sense? Yes, no? Then you have let equation star. So equation star is a list of all the operations, all the equations that happens inside of that function. So let's say you have f of x and y, wherein you have a temporary variable where you add x and y, you update the temporary variable to 1. So there are a lot of things happening inside of the function, right? So there is this collection of expressions that happen inside of this function. You have to understand all the little details of this JAX PR by equation star. That is the list of all the expressions that happen. And equation star again can be laid down to something called let var plus equals to primitive paraman expression. This goes on. So what I am trying to suggest you here is that it's very contrived and it's very dense. Once you look at a JAX PR, which we will, you will just take me out of the stage and you'll say, sure, I don't need this. You will. That is why I'm kind of trying to persuade you into understanding that, hey, this is going to be complex, but just stick with me, right? So coming to equation star, you have a lot of equations. All the equations will look like this, and this primitive keyword is used to understand that x equals to x plus y or x plus equals to y. Something like that can be broken down into two primitives. The two primitives are add and add, where x is being added to y first and that is going to be stored to x then later. So there are two primitive functions that happen step by step. So all these equations can be broken down into primitive operations. Make sense? Yes, no? Okay. And in expression star is all the atomic expressions or the equations which boils down to this last output step. Now this is a lot of things that we have covered in this illustration. The illustration is provided inside of the blog post. So anytime you are you make a JAX PR, you go to this illustration and quickly kind of try to understand what the similarities between the two things are. So your code, your expression, and our illustration. So what goes where? What we did here is we did build a demo function. We did make JAX PR. We have a JAX PR, and we also did the similarities for it. So what you can see here is def f arg1, arg2, arg3. Temp is equals to arg1 plus arg2. So temp is this temporary variable where arg1 and arg2 is added. Temp again is being multiplied with arg3. The output is temp by 3. Now inside of this make or the JAX PR, what we have is var star. So can you see any constants inside of the function? I don't see one. You can argue that 3.0 is a constant. The JAX does not take 3.0 as a constant. It needs to be a static constant. It's just a scalar for the time being, right? Yeah, it's just a number. So what we have here is that var star, that is the constants, is a list which is emptied. Hence there is just a box with nothing in it.
What could be an example of a constant?
I'm sorry?
Pi, epsilon.
In the function, how
Yeah.
would you? So the question is, number one, how would you define a function? A constant over here in the first function, and second, how would it look if it was there?
It would look something like that constant being introduced just after lambda, and as he said, if you want to scale your loss with some constant value which is being inside the subspace of JAX, like a JAX.pi or JAX.epsilon. So those are the constants which are already there in the namespace, and that gets called here. If you do a 3.14, that's not a constant again. Does that make sense?
So the constants are defined.
Yes,
inside.
inside of the subspace. Right?
And if you want to introduce any other constants, you can use default parameters. Right?
Does that make sense? Okay. Now moving on to var plus. Var plus are the input variables. So can you see that there are 3 input variables as there are arg1, arg2 and arg3. So these are all named as A, which is float 32, B, float 32, C, float 32 again. Float 32, the data types of all the arguments arg1, arg2, arg3. With me? Moving forward to equation star, that is the list of equations that we have. The list of equations are D, that is add A and B, that is arg1 and arg2 are being added. E is mul D and C, that means multiply D and C. So D is add A, B, and C is arg3. Does that make sense? F is E by 3. So you divide E with 3, and in, it turns out in is just one single value that comes out as an output, that is F, that is expression star. Everyone with, yeah, go ahead.
So suppose you have a function which is put as an argument in F. So suppose you have a function called A, which is put inside the argument of F. How would it look like over there? Would it be treated
So
as
you are talking about a closure.
I am not sure what it's called. But
Okay, so what I am seeing is def F, arg1 is basically another function called G.
Okay. So it is being treated as a variable.
It is, but inside of D, if arg1 is D, similar, D is here float 32, it's going to again make a lambda again of JAX here, because that is again a function. So it traces like a function again, right? So a function inside of a function.
Expand recursively.
I'm sorry?
It should expand recursively.
Exactly.
And that's kind of the bread and butter in neural networks because it's basically a composite function, right?
F of x of h of something. So a dense, car dense, car dense, car dense is an
How does it figure out the data type of ABC?
It infers from the output and also temp
Infers
by
from the output.
no, it infers from the entire thing. If I did a temp by 3 only, it's going to, first of all, it's going to be defaulted to F32, that is being used as JAX. Always takes float 32 as a default, but here also temp by 3.0 is something which it kind of infers to, that let's use float itself.
Output is similar.
Yeah, kind of.
Traces with
Yeah, traces.
Okay, everybody good to go? Now let's do the first functional transformation, that is JAX.grad.
So if
Yeah.
the output expression was returned to temp, if that by C was not present,
It would still give F32 because
it would default to.
Exactly, yeah.
But in that case, if that is the case, then it would.
yeah, it's not
It
optimized.
everything, no?
It's not optimized.
No, it is not.
It's not
And here,
optimized.
It would retrieve it, no?
yeah, that's true. And that is why, so the main idea behind JAX is that it's going to be used, how do I call it? It's going to be used on any accelerator. It's not going to be used as just something wherein you can use an int 8 or int 16. So it goes to a default of float 32, and then maybe if you use mixed precision or maybe you cast
I
it.
get that.
So that is the point.
Yes.
Was the question about type conversion?
Yeah. No, not type conversion. He said if you already defaulted to F32, it's already going to take a lot of space. So it's not optimized.
But you don't need always F.
But it will also retrigger tracing.
Yeah,
If I call that function on index,
Yes.
and then
Right. So, okay. So the first functional transformation, so the 4 functional transformations that are the power tools of JAX are grad, JIT, UMAP and PMAP. JIT is something which Shagdar took care of. Inside of TensorFlow, not in JAX, we'll cover JAX. But the basic idea is the same. You have an XLA compiler, you give a bunch of code to it, it compiles, it fuses a lot of things, it gives you a JIT compiled thing. But what I am trying to cover here is a functional transformation idea. The idea behind functional transformation in JAX is because JAX does not like objects. It does not, it always talks about functions. You have a function, you transform a function to another function. Functional programming, not object-oriented programming, right? So the first functional transformation is JAX.grad. It is very similar to what its parent did, that is autograd.grad, if you remember correctly. So what we do here is an equation of 4x to the power 3, 3x squared, 2x plus 1, and you make a JAX pair out of it. See how the primitive things are coming up, the primitive expressions are coming up. Now what we do is, we have also illustrated the entire primitive thing using a graph. So say A is the x here. You have 3 operations, x to the power 3, x to the power 2 and x times 3. You pass that A to build B, D, G and blah blah blah. Now how do I come to this illustration? How is this node created? It's created by the JAX pair. So what I and Ritwik did is get into a meet. I told him, like, iterated on the expression, he built the graph. That is how it is. Now this is going to,
I thought you folks use some word.
No, we were the model.
so now what we do is we pass this equation, that is a function, inside of another function called grad. So think about this very thoroughly. Grad, that is JAX.grad, is a function. It takes in a function, it transforms that function to another function. Lots of functions in a sentence that I used. So equation is a function, grad is another function. You have grad, you put in equation, it gives you the derivative of that equation. Now think about how simple it becomes. You don't have to use TF.gradient tape to get the derivatives. You have a function and you have a derivative as the function. Now a little caveat when I'm going into this, I love this bit very much by none but Matthew Johnson. He said it's the functional transformations are composable. Now think about what we just did. We have an equation whose first derivative is equation first there, right? That's the first derivation. If you compose that equation first there into another grad, you get the second derivative. You get the third derivative, fourth derivative, and so on and so forth. But in TF.gradient tape, you have got to nest a lot of things. The gradient tapes, tracing the gradient tapes are going to be a pain in the ass. I'll tell you, because this guy took my night's sleep by giving me GitHub gists of and letting me know that how do I do the third derivative of this. I said I can't. I just can't. Because there are a lot of it is.
Not just you can't, TensorFlow can't.
TensorFlow can't, right? So this is something wherein you have to understand that this really makes a lot of things easier, because we come from an engineering background where we have understood math first. So math talks about functions and derivatives as functions, not as gradient tapes, not as nodes, not as backward propagations from a loss node, right? We understand how functions are and how functional transformations work. So this is the entire max. Yeah.
Show me the PR already.
No question.
So
TensorFlow custom training loops, we can just remove the gradient tape and use the system. Can we do that?
what?
What did you just say? What did you just say?
Okay, so his question was, I understood his question. His
The
question
TensorFlow
was,
training loop,
Yeah.
the gradient tape. place the variance and all.
Ah.
So can I remove the gate dependent use case?
I am not sure. I haven't.
No, wait, wait.
No, so his
No,
question
you
was.
need,
Yeah.
you need, because you missed the
Exactly.
first one.
Ah.
The first equation was something of the cubic order, right?
Yep.
So when we find the derivative of that,
Mhm.
some terms go out. The
Yeah.
one becomes d by dx of 1.
Yep, yep.
But the JAX PR output becomes large. Why?
JAX PR output is actually the JAX PR of the functional transformation of grad itself. So grad, okay, how grad works. This is interesting. Be with me. Grad works by first tracing the entire function. Then, as you said, there are going to be outputs which are going to be transparent. Like we don't need that.
Yeah.
It's going to trace that entire function, remove them later. So what happens is something like this. The transparent nodes, can you see the transparent nodes? Those are something which we don't use. And I am very thankful to my colleague, that is Ritwik, who did this in 2 hours time. He created that graph all by hand, did the transparency equals to 0 stuff, and this is the graph that we have of the grad functional transformation. So it traces out the entire function first, and then it tries to figure out and fuse a lot of other stuffs, and then you have the output of the first derivative. Does that make sense now?
Where does fusion is occurred?
Actually, what happens is here there are a bunch of
Oh, okay. Got it.
B and E are not working,
Got it.
so
So they
it's
are-
not
So
going.
when you call G compile on it, it does the fusion.
Fusion
Show me
is
the code
optional.
already.
Okay, this works. Now the same thing again, composable. You have equation first there of 2. It gives you some value. Second derivative, third derivative.
What is weak time?
I'm sorry.
What is weak time?
Weak type is actually where you don't tell exclusively that you have to trace this.
Okay.
So it just gives you like an eager tensor
Okay.
inside tensor.
Hey, good question on that.
हाँ बोलो.
If that was a graph,
Of
I mean, in TensorFlow we get a graph.
this is Ritwik's graph. This is, you won't get it in anywhere.
He's asking what it is.
Oh, it is actually the graph of this matrix JAX sphere. That is the entire JAX sphere that you have. That is this
The
expression.
Traced expression.
Full traced expression
of the gradient.
of the gradient functional transformation. Make sense? Chalo. Now we come to a contrived example of JIT, and what we have with JIT is the steps that happens inside of JIT. JIT, again a checklist. Read the checklist while I drink some water. Define a function f, transform the function with JAX.JIT, run the function once. So what happens with running the function once is a warm-up step, where you just trace the entire. So remember what Shayaka told? First you have to TF.function, you have to trace that. Then you fuse it. So warm up inside of JAX is where you trace that. Then once it's traced, it also fuses on its own, and then you have this functional transformed JIT function that you can run, right? Matrix multiplication. You just have gnp.matmul.ab, that is the simple function. You have a key, you have A and B. Okay, we will talk about randomness a little later. But say, for example, this is just a pseudo-random key. This is just a key that is being used to create a random normal distribution. You don't need to know what keys are. You just know that this is one, right? A key, you provide that key to the random normal, you create 2 arrays or vectors, A and B of shape 1000, 5000, 5000, 1000, right? Now you make the JAX PR of matrix multiplication AB. The JAX PR is dot general. Thank God, we don't have a huge list of expressions. Now we time the entire matrix multiplication operation without JIT compiling. It comes to 252 milliseconds. And notice that this is not a GPU runtime, it is a CPU runtime that has this 252 milliseconds. Now JIT matrix multiply, JIT the entire matrix multiplication operation, functional transformation, yada yada, you have JIT matrix multiplication, that is a function that is JIT compiled, right? Make JAX sphere out of it. Can you notice something like a little contract here? This comes in. The JAX sphere lambda d, which is dot general. This is now under something called TJT. So it's a recursive kind of thing that happened.
And also answers his question.
And also answers your question that what happens if you provide another function inside of a function. When you use this same notebook inside of a runtime, the pjit will not happen. It will call XLA call, which is something where your GPUs are being used, brought into play. You have your XLA or TPUs. You have your
accelerators will come into play.
Exactly. Your accelerators come into, yeah, go ahead.
What if we have a function where we are taking a PNG key inside the function, we are generating a RNG key inside the function?
Another time. I need to ask.
Also, A and B are same because you are not generating a sub key, right?
A and B are not the same.
Because you are not generating a sub key.
No, the shapes are different, no?
Oh, shapes are different.
Yep. Okay, so warm up results, we warm that JIT function up. We also time the compiled thing. It comes down to 183 milliseconds, which is a speed up, but not so much so. And I'm not going to get you all excited with speed ups. It just happens out of the box. If you come to JAX, you already know the USP of JAX. It's speed, nothing else than that.
Transparency.
And also transparency.
And no, transparency and speed up.
Okay.
And no documentation.
And no documentation. So can we
And
cheat
my
everything, right? And can we cheat everything? So this question is something which, while going into JAX, me and Ritwik quite often came up with. Like this is insane. 252 milliseconds, 183 milliseconds, insane. Let's jig everything up. It does not happen that way. So what happens here is that if you have a function, if you have a condition where if x is greater than 0, return x plus 1, else return x. So it's a condition, right? You branch out your program executions based on this one single value, right? What happens if x changes? The branching changes. You have to retrace again, the JAX sphere builds again. Once you understand that JAX sphere is going to get built again, you understand that JIT is not going to work, right? What about it?
But that is only for the first time.
No, so if you think about that, so you have to give the same inputs to same inputs every time to x, no? If it's very specific to this x, where x is equal to 1, just for the matter of things, let's say that you JIT compile this function where x is equals to 1. So you are assuming that you are always going to input x is equals to 1. Other than that, it's not going to work because it's already traced that if x is greater than 0, it always knows that x is always going to be 1, which is of no use again. It's just one function which is JIT compiled. We can't condition loop that, right?
We cannot use ASTs?
We cannot use
AST?
abstract syntax tree. You can, like, I don't mind you going so deep into the Python code just for the sake of it.
I thought JIT uses AST. Like it just traces.
No, what happens with JAX is here where they have a wrapper called jnp.where where you can have conditions inside which it's not going to be static. So that is what it
flows is like kind of, that's how you do control flows.
Yeah. Now if you want to go into kernels, if you want to go into ASTs, I don't have a problem, but I don't want to go that deep, right? So yeah, it's very similar to tf.const as Shomik said. So jnp.where or something like that, where you can have the conditions. It's not always that conditions will break your JAX code, and it's not. Yeah, you have to be careful and also understand that there are provisions of not being a pure function. There are provisions, but you have got to be very careful while using those, right? So this is not a pure function, but because we are using a jnp.where, it makes it pure. Inside it might use AST, I'm not sure. I haven't gone into the repos so deeply that I understand every bit and piece of that. But that is how it works, right? And if you try this, you will get no exceptions, and it's going to work out the bad. Yeah.
You showed FL. Is it same for while loop and all?
Yeah. Any
control flow.
You also have XLA for loops. So XLA का compiler का for loop है, which is then like bubbled up to NumPy का for loop, JNP और NumPy का for loop. So you already have all the APIs defined where the edge cases can fall. So I'm going to cover VMAP and PMAP very quickly because after that we have a big session on how to use JAX into DL, wherein you kind of compress the numeric computation abilities to deep learning computation abilities. So I'm going to ask this right off the bat. So think about it, that your supervisor has asked you to write a code wherein he said that the input is going to be of shape, say X. Shape is X. That is, it's only going to have inputs of X dimensions, right? You took about 5 minutes, created that entire thing, have it pull requested, everyone gives a looks good to me, merges that, right? That's how it is. And 2 years later, someday your supervisor changes. He says, "What is this rubbish? I need batch now. I need batch inside of shapes." What are you going to do? And you 2 years later, so your code is lying between a bunch of other code which needs to be changed right from the scratch. What are you going to do? So what JAX did is, we have a VMAP functional transformation wherein you can provide that function that uses scalars. You just provide that to VMAP and you say that, hey, the batch dimensions are going to be 0. So inside of the JAX PR representation, it's going to provide that batch statement. So what happens now is that you have a transform function which can take batches right off the bat. How cool is that? Right?
Why did you define V that way?
Huh?
Why did you define V that way?
Define V.
Oh, okay, that's array. Yeah, I thought it was array.
Oh no, array. Right? And this is the same thing, like say A and B, just take 3, 5, the output is of shape 3. Next up, the batch A and batch B have 8 as your batch size and 3 and 5 as input dimensions. The batch output is 8 by 3. So it works right off the bat. Good to go. PMAP is where I'm not going to connect to a runtime. This is where you have a distributed setup. You have a distributed setup and you want to use that distributed setup. So what happens is, in distributed setups, you have these functions. You have to send those functions to each and every what do you call it? The hardwares, and they need to sync together. They need to have this distributed input system working in, and blah blah blah. So what happens with PMAP is that you have the same function, same singular function, let's say same, does not even take batches right now. You have the same scalar function, transform it into a distributed function, work that off the bat with all the TPU pods you have. It's going to work right off the bat. And a little interesting thing, due to the fact that all these JAX APIs are composable, like I said, VMAP, PMAP, JIT, GRAD, all of these are composable. So say for example, you are still that guy 2 years back who created this scalar function, and 2 years later you have this TPU pod coming in, as Shayada said, TPU pod coming in, free TPU pods, you need to work this out really quickly. You don't have batches as well. VMAP it, PMAP it. So it's going to be PMAP, VMAP, f of x. You first VMAP that, you have batches, you then PMAP that, you have distributed setup running right off the bat. Makes it simple?
And it also makes it scalable.
Yep. And the last bit is about randomness. So, how did we define stateful and state? Yeah, go ahead.
So you gave an example that I coded something huge code base, 2 years forward I am going to do this. So I will have to do this VMAP and PMAP for every function.
If the function that you are PMapping or VMapping is a traced function of all the functions above it, you don't need to PMAP or VMAP all the other functions. It's going to do it.
Pure.
Yeah, because it's pure, because JAX likes pure functions, it's already going to trace the entire stack of functions that has already been called inside of that function. But if that is not the case, you are going to individually
It's more work compared to TensorFlow.
It's more?
Work
No,
compared
no,
to
How?
less work.
No, it's less work.
How?
It's more scalable, less work.
If you had to do it by hand, you would have
3
switched
advocates
job.
versus 1 advocate of TensorFlow. Come on. Now, now randomness, a little bit of randomness. I'm just going to cover the basics. So remember a key that we introduced to all
Actually,
the
no. You can use tf.map_span.
TF dot,
Map_span.
and then
Just works the same way as we.
no, but inside of tf.map, what happens is that it does not.
tf.map_fun. I did not say tf.map.
So you're mapping that function to have another axis. I am not sure whether it's going to work or not.
tf.map_fun, not map.
Because what I do with mapfunc is that with the function being transformed into the function that you want, mapfunc, you also have to iterate that function over all the things that go into that as an input. So I'm not sure whether it's going to work or not. Yeah, or we could also do partial functions, that's for sure. But I'm not sure. But this is like API efficient and stuff like that. So it's easier to think about this. Right? Other than that, just covering randomness because he's going to cover a lot of things. Okay. So randomness. Remember key that is random.prng key. What happens here is that due to the fact that JAX likes pure state, it does not like stateful things. What we have is we have this key that takes care of all the generations of things which are random in nature. So if you provide this key into a random normal distribution while initializing it, and you provide the same key to the same function with the same shape, it's always going to give you the same results. It's not random. Beats the purpose, right? Why don't we have something random when you're talking about random? So what we have to do is we have to generate another key to make another set of random, you sample out from a random distribution. How does it help? So think about a deep learning program that you have written. You're going to show it to your boss, and you have this key generated, and you provide that key into the entire workflow. You know for a fact that this is going to be reproducible, because every random sample that has been created inside of the deep learning framework or the model that you create are already going to get sampled the same values that have been sampled while you trained it, while you inferred it, blah blah blah. So it's reproducible. And you also have this pure notion coming in, where things don't change. It is pure what it is. And how can you create different random numbers? Is by using random.split the key. So the key gets forked into 2 new keys or 3 new keys. You just have to specify how many keys you want, and you can get that key inside another sampling function. It creates another function. But think about it, if you create this key, you hold on to this key and fork it every time. You have this, how do you call it? The source of truth always in your hand, because it makes it reproducible, right?
Because this is JAX.random.split.
Yeah, it's alias. So that is the QR of, that is the QR of the second part of JAX. If you want to, go to this link, read it up, and you are very to university. Okay.
The link is there. The link.
The link is there in the slides.
अच्छा, ठीक है, चलो, right. This is JAX part 2. Right? So everything inside of here is what I tried to cover. And what we would really like you all to do is, if you want to go into JAX in more depth, read our blog posts and @PyMed search in Twitter and comment whatever you liked or whatever you didn't, because we always like iterating on people's comments or feedback. So yeah, that was me. I'll now give it over to Shamik.
Okay.
Or Rishi Raj first.